So the next thing we need to look at with our NMR analysis is understanding the multiplicities of our peaks. That is, we need to understand when and why we might have a peak show up as a singlet, a doublet, a triplet, or a quartet, like the peaks that you see here on this page. This first peak right here, this is what we call a singlet. This peak here with two lines where those lines are of equal height, this is called a doublet. This one is a triplet. So these doublet lines are a 1-to-1 ratio. In your triplet, the area under your peaks has a 1-to-2-to-1 ratio. This peak here, where we have 4 lines in the signal, this is what we call a quartet. And our quartet lines have a 1-to-3-to-3-to-1 ratio for the areas of those peaks. Now, what the multiplicity is really going to tell us is it's going to tell us about the number of equivalent protons on the adjacent carbons. It's going to tell us about the number of protons on the adjacent carbon. So when I see a peak in my spectrum that is a singlet, that tells us that there are 0 protons on the adjacent carbon. When I have a doublet, that tells me that there's 1 proton on the adjacent carbon. For a triplet, that will tell me that there are 2 protons on the adjacent carbon. And for my quartet, that will tell me that there are 3 protons on my adjacent carbon. So these are some of the most common peaks that we see in NMR, and as our structures get more complicated, our peaks will get more complicated as well. The number of protons that we see on the adjacent carbon is going to follow what we call the n+1 rule. It states that protons that have n equivalent neighboring protons will show n+1 peaks in their NMR signal. So if I look at the structure of bromoethane, what we already know is that we have 2 different types of protons in this structure. These protons at this carbon, I'm going to call HA. And what I already know about HA is that I have 3 protons in this methyl group. I know that I would expect for this signal an integration of 3. And I know that I would expect a chemical shift of about 1. My second type of proton in this structure are the 2 protons here, which I will call HB. And what I already know about the protons HB is that their signal will have an integration of 2, and they will have a chemical shift around 3 or 4 because they are bonded to a carbon that's also bonded to our electronegative bromine. So that's what I already know about HA and HB. Now, when I go to understand the multiplicity for the signals that I will see for HA and HB, we're going to look first at the signal for HA. So the signal for HA is going to be affected by the protons that we have called HB. Now, when we're analyzing our sample by NMR, we have an applied magnetic field that goes in this direction. And if we were to look at the signal for the protons HA, that original signal for HA, if it was unaffected by any other protons, would be right here in our spectrum. what happens is that the protons HB are going to generate small magnetic fields that will either enhance or oppose the magnetic field that our proton HA is going to see. Now, because we have two protons that we have identified to be HB, each of those protons can affect that magnetic field. If our protons HB work together and align themselves with the applied magnetic field in a way that they enhance that magnetic field, where both of them enhance, that's going to allow the protons HA to see a magnetic field that is enhanced with respect to the applied magnetic field. Now, along the same lines, our protons HB, they can also work together, but they can work together in opposition of that applied magnetic field, which is going to lower the signal that we would see. Or they can work in opposition of one another, where we have one enhancing the magnetic field, one detracting from the magnetic field, which effectively cancels. But we can have two combinations where we could get this impact. So the proton on the left could be up and the proton on the right could be down. And we could also have the other combination where this one is down and this one is up. So the fact that there's two ways that we can have this effect on the magnetic field of our signal for HA is what makes the peaks in our triplet have a 1 to 2 to 1 ratio. So that overall, our protons that experience this impact by HB will have a shift that's a little higher than what they would feel just due to the applied magnetic field. Our protons that see this impact by HB would feel the same effect of the applied magnetic field. And our protons that see this effect by HB are going to see a magnetic field that's a little lower than the applied magnetic field. So we have three ways that HA can experience a magnetic field. That's going to give rise to the three lines in our signal, which we call a triplet. So that overall, the signal for HA is going to be a triplet like this, where this peak corresponds to this peak in my triplet. This magnetic field, which we'll call 2, corresponds to this peak in my triplet, and this one is 3. So when we look at the signal for HA, we expect the integration to be 3, the chemical shift to be close to 1, and we also now expect that our multiplicity is going to be a triplet. So now we're going to look at the signal for the protons HB. And the signal for these protons is going to be affected by the proton that we have identified as HA. So we previously saw the impact of HB on HA's signal. Now we're going to look at the impact of HA on HB's signal. So what we know about HB is that there are two protons, so we'll expect an integration of 2. And we also know that on the adjacent carbon, there are 3 protons that we have identified as HA. So if we have the same applied magnetic field, and if my signal for HB with no impact from neighboring protons would occur right here, I'm going to look at what happens to the signal for HB as it is impacted by the protons HA. So there are 3 protons that we've identified as HA, and all 3 of those protons could work together to enhance the magnetic field. That's going to pull that line in the spectrum to a higher chemical shift. All 3 of the protons that we have called HA could work together and oppose the applied magnetic field. So we have 3 up and 3 down as our first 2 possibilities. But we also now have a combination where we could have 2 protons that enhance the magnetic field and 1 that opposes. And there's 3 combinations that we can have for this pattern. So we could have up, up, down. We could have up, down, up, or we could have down, up, up. And along the same lines, we could have two that oppose and one that enhance. So now we're going to have up, down, down as our first combination. Then we're going to have down, up, down, or down, down, up. So we have three that enhance, two that enhance, one that oppose, two that oppose, one that enhances, and three that oppose. So that when we look at these combinations that we have, these are all of the ways that HA can impact the signal for HB by affecting the magnetic field that our protons HB will feel. So what this means is that there's 4 ways that this can happen. And so we're going to have 4 lines in our spectrum, and our peak is going to specifically have ratios for our areas under those peaks that are 1 to 3 to 3 to 1. So that our signal for HB is going to be a quartet. So it's going to look like that, where we have a ratio for these peaks that's 1 to 3 to 3 to 1 that comes from the way that HA can impact the magnetic field of HB. So now if we look at HB, we know that our signal will have an integration for 2. We expect a chemical shift around 3 or 4. And we also now know that the multiplicity for this peak is going to be a quartet. If we were to look at this structure and apply the n+1 rule for our protons HA, remember that the n+1 rule tells us that protons that have n equivalent neighboring protons will show n+1 peaks in their NMR signal. So that for HA, when we look at the adjacent carbon, we have 2 protons. That means that we're going to have 2 plus 1, which is 3, which is consistent with that triplet we just looked at. For our signal for HB, we already said that we expected it to be a quartet. If we apply the n+1 rule, our protons HB on their adjacent carbon have 3 equivalent protons, so that means that the n+1 rule is going to be 3 plus 1, which is 4, which is consistent with that quartet that we expected. So if we look at the actual NMR spectrum for 1-bromoethane, here's the structure, and there are the HB and the HA protons that we previously identified. Let's start with HA. We said that we expected our protons HA to have a signal that integrates for 3, a chemical shift of about 1, and a multiplicity of a triplet. If we look at the data, there are 2 peaks in our spectrum, which is consistent with what we expect for the number of signals. We have a peak that integrates for 3 to represent HA. That peak has a chemical shift between 1 and 2. The chemical shift is a little higher than 1, but remember our protons HA are bonded to a carbon that's adjacent to a carbon that's bonded to a bromine. So it's reasonable that the chemical shift for those protons would be a little higher than our typical alkyl protons. As we look at the signal, we see that there's 3 lines in the signal. The signal is a triplet, and that's also what we expected based on the fact that we have 2 protons on the adjacent carbon, so n+1 would give us 3, which allows us to predict that that peak would be a triplet. So this signal is consistent with the data for HA. If we look at our protons HB, we said that we would expect a signal with an integration of 2, a chemical shift between 3 and 4, and a multiplicity of a quartet. So when we look at the data, here we have this peak with an integration of 2, a chemical shift of about 3.5, and we see in the peak that we have 4 lines, which gives us that quartet. So this peak here fits the data that we expect for HB.